नहीं, रोज सुबह करना था ना, नहीं रोज सुबह शाम आप निकल जाते थे, तब उसके बाद फिर से.
So let's start today's tutorial. So at first we will let me check is my voice is recording or not. So yeah, I think it is recording my voice. So now my today's plan is to talk briefly about the detail balance, and then I will solve the assignment problem which had been given previous year in the same course. So now why we need to know the detail balance. So first, in statistical mechanics, what can we do? We can only do the things with equilibrium, right? So equilibrium, but the definition of equilibrium is not so far clear to us. So let us define the equilibrium in a more clear way. So the definition of the equilibrium in more clear way is called detail balanced. Now apart from related to that any in statistical mechanics, what we do, we actually describe the motion of the molecular motion in a probabilistic sense or a stochastic sense, right? Now any molecular motions can be looked upon as a reaction, and so any molecular motion can be looked upon as a reaction. And what do I mean by the reaction? Reaction is nothing but a reaction that causes changes in the system. Hello, yeah, so that's it. So we can now we will define the equilibrium. So any molecular motion can be thought as a reaction, and the reaction is basically nothing but which causes a changes in the system. Now a simple example of a reaction, you can thought of a collision. A collision can be thought of can be a good example of a reaction where two particles come closer to each other and they contact to each other, then and then they just far apart from each other. So in this reaction, the changes is happening in its momentum. So suppose it's a particle 1 and it's particle 2, and after collision, suppose it is a v1 velocity and v2 velocity after the collision. Now before the collision, they will far apart from each other, and their momentum will be changed accordingly. So these could be thought as a reaction. So the interacting collision particle can be thought as a reaction. Now another example of a reaction, as you all know, the chemical reaction. And the chemical reaction is basically nothing, is a reaction in which the molecular combination of that molecule got changed. So got changes. So that is called actually chemical reaction. So a chemical reaction is nothing but chemical reaction. In a chemical reaction, what changes? The molecular structure changes. Molecular structure changes. Now as as we are saying that we will define the equilibrium in the form of detail balance. So what detail balance is actually is? So detail balance is, so detail balance basically implies the occurrence, implies that the in equilibrium, that detail balance implies in equilibrium that the number of occurrence of any reaction is in forward sense is exactly equal to the number of occurrence in the backward sense. What do I mean by that? Now this means actually when two particles collide with each other in the forward direction, suppose that their velocity after collision will be v1 v2, and before collision it's become the v3 and v4. Now by the detail balance means the number of process, that is the number of occurrence of this type of reaction, that means v1 v2 to v3 v4 is exactly equal to the number of occurrence, that is v3, a particle with velocity v3 collide with a particle another velocity v4, and after the collision the velocity of these two particles becomes v1 v2. Now the number of occurrence this reaction and this reaction will be exactly equal if, and this is called the detail balance. So the detail balance actually means it's not just the equilibrium in macroscopical sense. Macroscopical sense means from the larger scale, if you look at the system you will see no changes at all with time. So this is called the macroscopical equilibrium. So in terms of detail balance, as well as macroscopical and the microscopical, since this is the description of the microscopical description, so in detail balance not only the macroscopic equilibrium maintained but also the microscopic equilibrium also maintained. So that is meant by the detail balance. So now we know that the detail balance is a basic requirement of the equilibrium. So by when we are just say the system is in equilibrium, we mean that the system actually maintained the detail balance, means, and it's actually means that the macroscopic as well as the microscopic equilibrium is maintained, and that means the occurrence of any reaction, number of occurrence of any reactions in the forward direction is exactly equal to the backward direction. Now the same thing you can thought from the time reversal symmetry. Now this same thing, the detail balance, actually you can see from time reversal symmetry. Time reversal symmetry. Right. Now if you see at this equation, now in the forward direction, when time move in the forward direction in the flow of time, in the direction of the flow of time, you see that the v1 and v2 interact with v3 and v4, right? And suppose that you see it n1 number of times in your system, and when just you reversed your system, you just looked at reverse direction of the time, you will see that not v1 v2 actually collide, but v3 v4 actually collide with each other, and v1 and v2 velocity will be produced. And what is the number of occurrence? That will be actually basically same n1. But now in your system, since the detail balance is there, so that means at the forward direction, at when you just move in the forward direction of the time, you will see not only this v1 v2 goes to v3 v4, but you see v3 v4 also goes to v1 v2, and the number is exactly equal. That means when you just time reverse, suppose a system is in equilibrium, suppose a system is in equilibrium PM, and that means its time reversal state should also be in equilibrium. Also be in equilibrium. And this will only happen when at the microscopic level the detail balanced will be hold. So that is why we need the detail balance. Okay, now we know in ideal gases, as we know, for ideal gases, if the collision is not present there, that is from our definition of this detail balance or equilibrium, a reaction should be there. That means a collision should be there to begin with. If we want to define some equilibrium, and we know in thermodynamics we actually deal with this equilibrium at equilibrium. So those we deal with those quantity which actually at in equilibrium, So that means if in a gas then there is no collision, if in the gas there is no collision at all, this implies the state of these gases will not change. That means the molecule will not be moved at all. That means no thermodynamics. So if the gas are not colliding with each other, then there will be no thermodynamics. So the collision is required. The collision is an basic ingredient of the thermodynamics. Okay, now so this is the things. Now when we call a gas is an ideal gas, so to when a gas actually behave like an ideal gas, so to do so there is two things that gas should follow. One, that the collision time is very short, relative to the that in a box, if the gas one gas molecule is moving around and sometimes it gets collide, so that means the time it takes for collision with two particles is very short relative to the time it's moving around or roaming around to these whole boxes. So that means collision time should be very short relative to the roaming time of the particles. And second things, the collision diameter, that means the diameter means a particle when just got interacted with another particle. Suppose that if two particles radius are r1 and another particle of radius of r1, that means if these two particles are at far apart from 2r, if the distance between these two particles is more than 2r, if the distance between these two particles are more than 2r, then these two particles will not collide with each other. That means these two are is these two particles collision diameter, and the collision diameter of these two gas molecule should be much less than, should be much less than the volume of the total gas particle, total volume of this container, volume of this container, or the total space in which these molecules are roaming around. So if these gas molecules follows these two kind of things, then these gas molecules we can call it as an ideal gas. Now from the concept of detailed balance, we will deduce the formula for the fermions. The occupancy number, that occupancy, which is occupancy number, we already know that the occupancy number means in the state K, the number of particle on average remain on the K state will be 1 by 1 plus e to the power alpha plus beta epsilon k, where epsilon k is the energy of the kth state. So we want to deduce this occupancy number for fermions and bosons with using this concept of equilibrium, or called detailed balance. So let's do it. So suppose that two fermions, in case of fermions, when two fermions interact with each other and they will exchange their state, that means they will here for the fermions, we know that for the fermions or the quantum particle, the energy and the momentum of two particles can be means we can know from its know from the state in which these fermions are. So that means if we know the state of the fermions, we actually can calculate the energy and momentum of the fermions. So that means when two fermions are interacting with each other, they actually exchange their state. That means it is legitimate to call that things a reaction. So that means if two fermions, suppose 1 and 2 are interacting with each other and they change their state between themselves, and after the interaction the state of these two particles become 3 and 4, right? Now this is called a reaction. Now what will be the probability that this reaction happens? So let's see that. Suppose that the probability a single particle at state 1 is f1 and at state 2 is f2, similarly at state is f3 and state 4 is f4. Now before the collision or interaction happens, we need the two particles are sitting at the state 1 and 2. That means the probability of happening that event is f1 into f2. So f1 is the probability of particles sitting at state 1 and f2 is the probability that particles sitting at f2 2. Now after that, these two particles should go to the state 3 and 4. So that means what is the probability that it will happen? So it will happen that these two particles should be there in state 1 and state 2. That means the probability the two particle that means this one there are lot of interaction could be there whose final state could be 3 and 4, but what is the probability that this state 3 or 4 actually came because of this reaction? That to write that probability we have to the probability of this state f1 into f2 and the probability of f3 and f4, but we have to keep in our mind that since these particles are fermions, that means these two particles cannot collapse to a single state. So that means it cannot happen, this process F2 and F1 and F2 cannot collapse to the process F3. So we have to just negative of F1, F2 and F3. And there are another thing is there. So this process that 1 and 2 cannot, two particle cannot collapse to a single state F4, since this is up, since these particles are actually fermions. So that means we have to also deduct from these things F1 into F2 into F4. So that means this will be the probability of happening from happening that reaction. But one thing we have to keep in mind that since this is a quantum mechanical thing, so these from going to 1 and 2 to 3 and 4, the state 1, 2, 3 and 4, there will be some transition probability, and that will be denoted by R. So now you can write it in this way. If we simple it, if we take common F1, F2 from each term, so it will be 1, so this will be plus F3, F4, this will be minus F3 minus F4 into R, F1, F2, another 1, so this could be write as 1 minus F3 into 1 minus F4. Now you can see from this expression, you can think this in another way, that is the probability that if two fermions are sitting there in 1 and 2 and they got collide with each other, then the state will become 3 or 4. That means a particle should be sitting at state 1 and state 2, and since these two particles will be go to the state F3 and F4, that means this state should be this state should not be should not, some other particles should not sitting at the 3 or 4. So that means we have to calculate the probability that the 3 and 4 is empty. So if F3 is the probability that a particle sitting there, so 1 minus F3 is the probability that the 3 and 4 is empty. So that means one particle here, one particle there, and there are no particles at 3 and 4. So that means this is that probability, and R is the transition probability, that what is the probability that from 1 and 2 it will go to 3 and 4. It could go to another state, but what is the transition probability that it from 1 and 2 it will go to 3 and 4. And now you can see this comes from this we will get this from by solving the Schrödinger equation IH del psi del t equal to H psi. So if we solve this equation, we'll get R. Now another thing, since from the detail balance we know that if this system is in equilibrium, then the detail balance should be followed. That means the rate at which these 3 and 4 goes to 1 and 2, the rate at which the 3 and 4 interact and produce 1 and 2 state should be same. So in the similar fashion, we can write the rate at which the 3 and 4 the particles sitting at 3 and 4 interact with each other and their state becomes 1 and 2 will be simply F3. One particle should be sitting there, one particle should be sitting there, no particle should be there in state F1, no particle should be there in state F2, and a transition probability R dash. But so that means this for the detail balance, to follow detail balanced, these two things should equal F2, these two things. So F1, F2, 1 minus F3, 1 minus F4, 1 minus F3, 1 minus F4 should equal to R into F3, F4, 1 minus F1, 1 minus F2 R prime. Now one of the beauty of the quantum mechanics is that these time evolution of the quantum mechanics actually by principle is poses a time reversal symmetry, by which I means that if we want to know the backward trajectory of this psi, we have to write del psi del t psi is equal to h psi. This is the forward motion. What will be the backward psi? Backward psi will be nothing but minus I h gut del psi star del minus t h dagger and psi star. And we know the h, since the h Hamiltonian operator is a unitary operator, so that means h dagger means h, so that means h psi star is equal to I h cut del psi star del t. Now you can see from here that this psi star and this psi star and this psi star actually follows the time reversal symmetry. That means these two quantity, that means r, should be equal to r prime, because you can see this state is nothing but the time reversal state, time reversal reaction of this reaction. That means, and since that the quantum mechanics Schrodinger equation poses the time reversal symmetry, that means r should be equal to r prime. So from this equation we can write it f1 by 1 minus f1 into, we just take this and these two in this side and these two in that side, and r, since r equal to r prime, so these two got cancelled out. So f1 f2 and f2 by 1 minus f2 is equal to f3 by 1 minus f3 into f4 1 minus f4. So now you can see that for two particles interacting with each other we get this relation. Now it is easy to see that for three particles, this is two particles, and for three particles this relation will become f1 by 1 minus f1 into f2 by 1 minus f2 into f3 1 minus f3 is equal to f4 1 minus f4 into f5 1 minus f5 into f6 1 minus f6. By three particle we means the reaction will be like that: 1 plus 2 plus 3 will be 4 plus 5 plus 6. Now from these two equation has one solution, that is fk by 1 minus fk is some constant, and it is equal for every state. But these seems somewhat not feasible at all, right? Because you can see that the probability, occupancy probability does not depend on the energy, so this should not be the case. So what should we take into account? We should take into account the two constant of motion, which is the total number of particles and second thing is total energy. So total number of particle and total energy is equal, means the energy of the particle at 1 and 2 should be energy of the particle 3 and 4, and the particle number is 2 should be conserved, and similarly for the 3 particle case, this is for the 2 particle case, and for the 3 particle case, the total log of particle is 3, and total energy will be epsilon 1 plus epsilon 2 plus epsilon 3 should be equal to epsilon 4 plus epsilon 5 plus epsilon 6. So these total numbers should be conserved. Now we know the what value should this constant possess. So one solution of these equations will be fk by 1 minus fk is e to the power minus alpha minus beta epsilon k. Now you can see that if there are suppose that n particle is there, then so I equal to 1 to m fk 1 minus fk. Suppose that m particle interacting with each other will be equal to by I equal to m to 2m fk 1 minus fk, and from here you can calculate this will be minus m alpha minus beta summation of k epsilon k equal to e to the power minus m alpha. Here if you calculate it, it will become a minus beta summation of epsilon k. Since the total number of energy should be conserved, that means this is an solution, this is a solution of that equation which follows these two conserved, these two constant of motion. That means from here it is easy to see that what will be the occupancy number, that means what will be the fk. So we got the fk by 1 minus fk will be e to the power minus alpha minus beta epsilon k. So we can write it epsilon k by fk will be e to the power alpha plus beta epsilon k, which will be 1 minus 1 by fk equal to e to the power alpha plus beta epsilon k, which will be 1 by fk sorry, this will be this will be actually 1 by fk minus 1. So that means a 1 by fk equal to 1 plus e to the power alpha plus beta epsilon k. That means fk will be 1 by 1 plus e to the power alpha plus beta epsilon k. So now you can see that we consider nothing, only consider one thing is called detail balance, detail balance, and second things the take into account the conserved quantity, and if we means by the mechanism of detail balance and the property of the fermions, the occupancy number that I have written here 1 by 1 plus e to the power alpha plus beta epsilon k is actually automatically come up from the detail balance, and from the detail balance if we follow the detail balance, if the system of fermions where the total number of energy and total number of particles conserved, if that follows the detail balance, the occupancy number in equilibrium will be automatically come. So that means the equilibrium which in the thermodynamics, which equilibrium we are talking about is actually the equilibrium that is because of detail balance is followed in the microscopic level. So that equilibrium we are whenever we talk equilibrium in thermodynamics, we actually talk about the detail balance. So that is the things. Now in the similar manner we can also deduce the occupancy number, or it is fk is for bosons also. So it will be 1 by 1, it will be 1 by e to the power alpha plus beta epsilon k minus 1. So to do so, we know only we have to write cleverly the probability of this happening this reaction, and we already know the rate at which these things happens since the quantum mechanics follow the time reversal symmetry. This forward reaction rate and the backward reaction rate will be cancelled and the remaining things will be these things. So we have to calculate these things for bosons by applying the property of the bosons, right? So if suppose there is a two particle 1 and 2 got interacted with each other and they change the state to 3 and 4. Now what is the probability that this kind of reaction will be happen is that the probability of happening this state will be f1 into f2 and plus what will be the probability that 3 and 4 comes from the 1 and 2, which will be f1 f2 and f3 f4. And there will be another things also, that these two particles can collapse to a single 3, that means f1 f2 can also be like this, and these two particles can also collapse to the in the state 4, that means f1 f2 into f4. If we take common f1 f2, we'll get 1 plus f3 and 1 plus f4. Now this is the forward process. Similarly we can write also the backward process, and from there we'll got a expression like that fk by 1 plus fk should be constant. And again, if we apply the constant of motion, we know that this quantity is nothing but fk by 1 plus fk is equal to the power minus alpha minus beta epsilon k. So from here we know that fk will be 1 by e to the power alpha plus beta epsilon k minus 1. So again, in the similar if we follow the similar step as we did for the case of fermions, we will actually easily got the result that is what is the occupancy number of for the boson gas by mean the occupancy number by occupancy this number. That means what is the occupancy number? Occupancy number is nothing but the probability of a particle will be at state k is the occupancy number of that boson. So now we know that what is the occupancy number of the bosons and fermions, and we have calculated it from the very basic principle called detail balance. So that's it. Now we are going to solve the previous year questions that had been given and in the assignment. So let's solve that. So take the first question. So this is here. So this is all about the equilibrium. So since I feel that the notion of equilibrium in statistical mechanics is something we all have to know. So we have to know it's clearly what the equilibrium means by the word equilibrium, what actually means by equilibriums, and what is happening on the microscopic level when we say that the system macroscopically is in equilibrium. So So because of that, I am revising this equilibrium and all the calculations for the occupancy number, as well as you can, in a similar manner, you can also calculate the total number of energy, total energy of these particles. Now let's move to the question solving part. So let's see what the question number 1 is saying. Okay, so insert the question number 1. Okay, so here the question number 1 is. So what is the question number 1 is saying? Okay, in the question number 1 it is asked that the degeneracy pressure of an ultra relativistic Fermi gas in 3 dimensions may be written as P is equal to rho to the power n. Okay, so we have to calculate the degeneracy pressure. Whenever you will heard this word degeneracy pressures of Fermi gas, you should calculate the pressure at T equal to 0. That means beta is equal to infinity. Now we know the rule, the formula for calculating the pressure. So let me check it. Yeah, so the formula for calculating pressure is 2y beta V is the volume, B is the inverse temperature, it is the inverse temperature, sum over the all of the states 1 to infinity, log in the natural base 1 plus e to the power minus beta epsilon j, beta minus epsilon j minus mu. Okay, so let's look at this term. So e to the power minus beta epsilon j minus mu, limit beta tends to 0, because we have to calculate the pressure at beta tends to infinity. Beta tends to infinity, that means T tends to 0. So if epsilon j greater than mu, that means this term is positive, and that means this whole term beta epsilon j minus mu is positive, and this is e to the power minus infinity, and e to the power minus infinity means we know it is 0. So that means for epsilon j greater than mu, this term becomes 0, and for epsilon j less than mu, let's calculate what it is. For epsilon j less than mu, so if we put epsilon j less than mu, that means this term beta epsilon j minus mu will be negative, and if beta epsilon j minus mu will be negative, that means this term e to the power beta minus beta epsilon j minus mu whole term will be positive. So that means e to the power beta epsilon j minus mu mod of beta epsilon j minus mu, and that means this term will become infinity. And if it becomes enormously large, then this 1 can be neglected with respect to this term when epsilon j less than mu. That means we only left with the terms 2 by okay, so we only left with the terms p equal to 2 pi beta v summation of j equal to 1 to infinity log of e to the power minus, so minus, actually you can absorb the minus beta mu minus epsilon j, because mu is greater than epsilon j, so this term is actually greater than 0, and this whole term is much larger than e to the power beta mu minus epsilon j is much greater than 1 at limit beta tends to infinity. So that means we left with these two terms, and we can calculate, it is very easy to calculate that this will become 1 to infinity log will be beta mu minus epsilon j. So that is nothing but 2 by v summation j equal to 1 to infinity mu minus epsilon j. So this will be, so at t equal to 0 the pressure will be 2 by v j equal to 1 to infinity mu minus epsilon j. Now we have to write, since we have to do it for ultra relativistic Fermi gas, so we have to write the energy of the Fermi gas in it will be p square c square plus m0 square c to the power 4, and we know p equal to h cut k, that means it is nothing but h cut square k square c square plus m0 square c to the power 4. And similarly you can write mu as, mu means the Fermi energy, mu is equal to root over of h cut square kf square c square plus m0 square c to the power 4. Now since we have, in this question it is asked we have to calculate in the ultra relativistic limit, that means this term is much greater than ultra relativistic limit, means h cut square k square c square will be much greater than that m0 square c to the power 4. So we can approximately write epsilon j as h cut k c, so h cut k c, so we can write it h cut kc, and mu will be h cut kf into c. So it can be approximately written, we can write as. Now we know that this summation can be replaced by integration. So, and to do that we know that we have to assume that this is these particles are contained in a box whose length actually whose length of this each side of the box is actually enormously large enough. So that's why we can approximately write this summation as an integration when the side, each side of the box is enormously large, the box where we put all the particles. So then we can write pressure is equal to basically pressure is equal to, so pressure is equal to 2 by v integration, so dq x is the position coordinate and dq momentum into this energy will be, momentum will be 0 to pf, and this will be dqp and dqp mu minus epsilon, and we know that epsilon means that's h cut p. And we again, if we write, we know that dq, and it is the volume integration, another is volume integration. So if we integrate over the volume we get a volume, so this volume cancelled out, so we left with pf, and it will be 4 pi p square dp mu minus epsilon p. Now if we write p is equal to h cut k, h cut k and epsilon equal to h cut kc, we could write it as p is equal to 2 by 2 pi q 0 to kf dk 4 pi k square mu f minus root over of minus this can be c will be simply, so mu f we can replace mu f by these things, the dk h cut kfc minus h cut kfc minus c h cut k. And if we do this integration, if we do the integration, we'll got 2 pi cube 0 to kf 4 pi dk k square h cut c kf minus k. So we write it outside 8 pi h cut c by 2 pi cube 0 to kf dk kf k square minus k cube. And you can easily calculate, it will be nothing but it will be simply, okay, let me do it. 8 it cancelled, so h cut c by pi square will be there, and there will be, so this integration will give me kf, this will be k3, so k to the power 4 by 3 minus this will be kf to the power 4 by 4. So that will c h cut by 12 pi square kf to the power 4. Now we have to write it in terms of rho, pressure, rho, the density of the gases, and it's come out as a function of kf square. So we have to calculate the density of state. So we know the density of state is sum over all state 1 to infinity. It will be 1, this will be 2, this should be 2 by v, right? This should be 2 by v, 1 by, this should be 2 by v. These two comes from there are from the spin degeneracy, so no worry about this spin. Spin comes from spin degeneracy, because there are a spin up and down is there. So total number of particles, so nj, it will be 2 by v summation of j equal to 1 to v. So total number of particles by volume is actually the density of the particle. So 1 by e to the power beta epsilon minus mu my plus 1. Okay, since at the limit beta tends to infinity, when epsilon become less than mu, this term actually, this epsilon, so here a minus will be there, right? So there is a minus term should be there, right? So when beta equal to infinity and epsilon less than that, okay, epsilon less than that, okay, it will be e to the power beta epsilon minus mu plus 1. So when epsilon less than mu, at beta tends to infinity, epsilon less than mu means beta epsilon minus mu become less than 0. That means at beta tends to infinity, when e less than mu, beta epsilon minus mu should goes to 0, and this become 1. And if epsilon become greater than mu, that means plus beta epsilon minus mu become greater than 0, and e to the power beta epsilon minus mu will become infinity. And if it becomes infinity, the whole terms will become 0. That means the only contribution will come from when f such j less than mu, and that contribution will be 1. And now if in the similar manner as the previous, if we consider the gas are in a large inner box, that means the length of the side of the box are enormously large, then we can approximate this summation by integration, and we can write it as 2 by 2 pi cube 0 to kf 4 pi kf square dk. So 4 pi k square dk, and from here we can easily write 2 pi cube, it will be 4/3 pi kf cube, which will be the kf cube by 3 pi square. And if we invert it, then we'll got kf will be 3 pi square into rho to the power 1/3. Now if we put this value of kf here, we will get p actually proportional to p proportional to kf to the power 4, and we know that kf proportional to rho to the power 1/3, that means it will be p proportional to rho to the power 1/3 to the power 4 should be rho to the power 4/3. So that means the pressure, we can write pressure pressure proportional to rho to the power 4/3. And as in the question it is asked, if we can write the pressure in terms of the density, what will be the power n? Now we know that the power will be nothing but 4/3. So that is, this is the 4/3. Since we get the power will be, what will be the power? Power will be nothing but 4/3. So we actually get what the power in equal to 4/3. So this is the answer of this question. So that's that. Now let's move toward the next question. So okay, toward the next question. Yeah, so this is the next question. So let's do it, the next question. Okay, let's do the next question. In the next question it is asked the value of 0 to epsilon uq epsilon d epsilon, where u epsilon obeys the Lane-Emden equation. So let's write what is the Lane-Emden equation. Let me check. And okay, so what is the Lane-Emden equation? Lane-Emden equation is 1 by xi square d xi of d xi of xi square du dxi is minus uq xi. So this is the Lane-Emden equation which has been taught in the lecture. So now if we do a little bit algebra, left hand side can be write as 1 by xi square. Now d xi of xi square into d xi of u plus 1 over xi square into xi square. I am doing nothing, I am doing just nothing. Basically I just differentiate these two terms by the rule of multiplication, Leibniz multiplication rules for differentiation. It's a square into d of dxi du dxi. So we can write it like that, equal to minus uq xi. Now from this step you can see we can d xi of xi square equal to 2 xi, so that means 2 by xi will be remain there, du d xi plus 1 by xi square. So this xi square cancel out. Only term that we are left with is du d xi minus uq psi. Now you can see by doing this what I want to go, because I need xi uq integration, so I will take xi to this side, so 2 du d xi into d xi du d xi minus xi uq. Now you can see that we got this term xi uq xi. Now let's integrate both sides, 0 to xi 1, 0 to xi 1. We have to calculate this quantity. Now if we calculate only this quantity, then we can say that the u xi which obeys the Lambda equation, whose integration 0 to xi 1, xi uq xi will be equal to this quantity. So let's calculate this quantity first. So this, if we calculate this quantity, this will be 2 0 xi 1 du d xi 1 d xi, sorry, a d xi is missing there, whole will be d xi, there will be d xi plus 0 to epsilon 1 xi, too many, xi d xi of du d xi. So this quantity is straightforward, this is actually, this integration is straightforward, it is nothing but 2 into u xi 1 minus u 0. Okay, and we will integrate by parts this quantity xi, and this quantity will be du d xi, right, by part. So this will remain unchanged here, and we integrate this, if we integrate this out, the term will come du d xi, so it will to 0 to xi 1. Okay, second term minus 0 to xi 1. First derivative of this term, if derivative with respect to xi will be 1, that means integration of this term will become du d xi, integration of whole this term will be du d xi, and one integration left, so that means d xi. So you can see that these integration are same, so it will become 1 will be this part, so the integration of this will be same as u xi 1 minus u 0, so these two will become same, so 1 will be cancelled, the left will be du xi 1 minus u 0, and from this term we'll get xi 1 u prime xi 1 minus another thing will be, if we put 0 there, the whole term will become 0. Now you can see that the negative of 0 to xi 1 xi uq d xi will be this quantity. Now what will be the value of 0 to xi 1 uq xi into xi d xi will be negative of that, means minus xi 1 u prime xi 1 minus u xi 1 plus u 0. So that's it. Now we got our answer, which will be the answer Now fourth one will be the answer. Xi1, let's check, minus xi1 u prime xi1 u prime xi1 minus u xi1 plus u0, right? So that means this will be the answer of that question. So now we have solved the question number 2. So the answer will be the fourth one. So now let's move toward the question number 3. So let me insert the question number 3. Question number 3. Okay, let me do one thing. Other way it will come in random places. So okay. Okay, yeah, it is. I hope this is, you can see it clear. Oh, so that's it. Now in question number 3, what is asked, that if I nu d nu is the energy density of radiation in a black body of temperature T between the frequency nu and nu plus d nu, the value of the integral 0 to nu d nu is, okay, we have to calculate these things. So we know from the lecture that I nu is basically nothing but, let me check from my note, so it is 8 pi h nu q by c square, so d nu e to the power h nu by t minus 1. Here we always assume in the class it's always assume k beta equal to 1. For all the calculation we always assume the k beta equal to 1. Kb means Boltzmann constant. Now what we have to do, we have to do the integrate it from 0 to infinity multiplied by nu I nu, okay, d nu is there, I nu t nu. Now so 8 pi h nu q c square into, okay, this is there, so nu we have to multiply by nu again, d nu by e to the power h nu by t minus 1, 8 pi h c square 0 to infinity nu to the power 4 d nu e to the power h nu by t minus 1. Okay, now let's assume h nu by t is equal to x, so we can replace nu by nu is equal to t by h into x. So let's replace it here, 8 pi h c square 0 to infinity t by h to the power 4 into x to the power 4, and d nu means, here if you calculate d nu you will get t by h dx, so that means put it here again, t by h dx, and here e to the power x minus 1. So what is left with us, 4 pi h c square t by h to the power 5 0 to infinity x to the power 4 dx by e to the power x minus 1. So after this tedious looking calculation, we just got this cute looking expression. Okay, now from here what can we tell, 8 pi c square h to the power 4 t to the power 5 into this will be some constant, so there is no dependence, this will be some constant. So x to the power 4 dx e to the power x minus 1. Don't worry about these things. So all these type of, if in some exam, some competitive exam, if this type of integration they asked for calculate this type of integration, they will, in the question paper, they will always provide, means at least they should provide the answer of this integration. This is actually this the result of this equation will integration will be 2 to the power 5 zeta is zeta, the crazy looking zeta 5. So this is zeta function, don't worry about it. So they always provide you this function, but the main thing you should notice here is the dependence, how it depends with temperature. It depends with temperature t to the power 5. This kind of questions is actually things t to the, this depends on t to the power 5 and how it depends on h to the power 4. So you can look in this answer, you can tell that only these two, t to the power 5 h to the power 4 is there and t to the power 5 h to the power 4 is there. So these two answer can be there, and since we know x to the power 4 dx e to the power x is 2 to the power 5 zeta 5, that means this is actually zeta 5. That means which answer should be the answer? This answer actually the answer. So 190 pi t to the power 5 zeta 5 c square h to the power 4. So I think it poses some error. The factor should not be 192. It should be 8 into 2 to the power 5. It should be like that. So that's it. So that is the question number what is the question? Question number 3. Now let's move toward the question number 4. Again, that question is very simple. Okay, let me put it here. Question number 4, right? Question number 4. Okay, so question number 4. So in question number 4 it is asked that if a double the frequency and double temperature, the value of I nu. So it's very simple question. All we have to do, that we have to write the formula of the expression of I nu, the intensity, the intensity of radiation of frequency nu that is emitted from a black body of temperature T is I nu. So 8 pi, so h nu cube by c square. I am writing it from directly looking from my notes, because no way to remember these formulas. You can always derive these formulas, but it's very tedious job. So in exam, I, from my personal view, they should always provide this type of formula in the exam paper. So I nu equal to 4 pi h nu equal to c square d nu e to the power h nu by kt by kt we assume kt equal to 1. So that's that h nu. Now we have do what things? We doubled the frequency. Nu prime will be 2 nu, and double the temperature. So this should possess a temperature sign here, because at temperature T, this is the formula for I nu T. So temperature, we double the temperature. So if I put it back here, so what will be my intensity of the radiation with frequency nu prime, which is emitted from a black body whose temperature is T prime, is 4 pi h c square 2 cube, so 2, so sorry, so this will be 2, not 2 nu prime cube into d nu prime is not there, right? So d nu prime is not there. I nu, change in I nu, so 1 by e to the power, so h nu prime by t prime minus 1. Now if we put these things, we got h by h c square nu cube into 2 cube means 8, and 1 by nu prime by t prime will be nu by t, so e to the power h nu by t minus 1. So that means 8 into 8 by h c square nu cube into 1 by e to the power h nu by t minus 1. And from the above expression we know this is nothing but I nu. So that means if I double the frequency and double the temperature, the value of I nu will be increased by 8-fold, right? Increase by 8-fold. So that's it. So this is the question 4. Now we will solve the question 5. Let's do it. Okay, sorry. Let's do it. Solve the question 4. Insert. Question 4 we have solved. Question 5. Let's question 5. It's another a simple question. Again a simple question. Okay. So let me solve this question. Now here it is asked, a black hole has a temperature because it is hot due to the gases spinning around it. It is exchanging energy with the surroundings. It has both entropy and internal energy. The radiation from nearby and faraway stars are shining on the black hole. Now, to solve this type of question, you should always keep in your mind that what is the definition of the temperature is. Now you have to go back to the definition of temperature. Now what is the definition of temperature is actually del S del E with pressure and volume constant. Right now, if we know the definition of temperature, by looking at the definition of temperature, you can tell something that if some system possesses some entropy and possesses some energy, and if its entropy depends on the energy, that means there will be del S del E non-zero, then there will be some temperature, right? So from the definition we know that if there is for a system, if there is an entropy, there is an energy, and if the entropy depends on energy, then we can say that the system possesses some temperature. So that means the answer of this question will be, since a black hole possesses both entropy and internal energy, that's why we can say that this system, a black hole, has a temperature. So that's all. So question number 5. Now we will solve question number 6, which is a little bit involved. So we'll start from the basic concept. So let me insert the question number 6. Okay, this is question number 6. Yeah, question number 6. Okay, question number 6, insert. Okay. Question number 6, that's it. This is the question number 6. Yeah, so let's do it. So after solving it, I want to solve it from the basics. So here it is asked very simple questions that the time required for a black hole of mass of tennis ball 50 gram to evaporate is approximately. So how much time is required to evaporate, right? So let's calculate that. To calculate that, what things we need? So what things need? How can a how can a thing evaporate in means how sorry how does a thing evaporate in the air? That means its mass should decrease with time. That's how it will vanish and it will evaporate, because here it is not evaporate in air. I'm sorry, it's evaporate not in air but evaporate in the vacuum space time. So how can it be, right? So a black hole not only absorb all light which just come into it, all light, all matter come into it, but it's also radiates something. Why it is radiates? So let's see first why it radiates. So black hole basically nothing but all the material that was there will be collapsed to a single point because of strong gravitational pull. Now around that point, that singular point where the all must squeeze into a point, this is called the singular point, and outside that point there is a radius called event horizon. Outside the event horizon there is a no harm, so all the space, all the things are similar, is the similar as other things or other stars. But when things or radiation or particle just cross this event horizon, the gravitational pull will become so large, so enormous, that all the things eventually go towards this singularity. And in another involved term, you can involved term will be for that all the space like event will become time like. So inside this event horizon all the space like event become time like event, and outside there is space like event. What do I mean by that? That means, suppose that space like event means, suppose that there are 2 points separated by a distance. Suppose that they are separated by 5 semi. Now one individual can move, one individual go towards that and can avoid these points. Suppose this point A and this point B. Suppose an individual will move towards a light or something which will move towards B, and they can move around this point like this and they can avoid this point, right? So this is a point B. So anything which is apart space like distance, suppose 5 centimeter, they can always avoid this point by moving around that point. Okay, that's it. But suppose that there are 2 points are there. Suppose there are 2 points are there which are time like. That means that point A and B are far apart like 5 minutes. Can A avoid the B? No, there is no possible way that can avoid avoid the point B, because this is the fate of the particle that after 5 minutes it will reach to B. Like suppose that you can avoid you can avert a point in which is separated space like, but you avert the Monday, or you can avert the next week, or can you avoid the next year? You can't avoid the next year, because it is, I mean, the trajectories will always go to the next year. That means when the distance become time like, there is no way to go around it. You have to fall on that point. That is why when a particle or things just crosses the event horizon, it becomes, the distance between that particle and the singular point become time like. And since it's become time like, because for this person this point is like Monday or next year, so it will eventually go to the next year. It's not like point in the space. So that's why all the things inside the black hole collapse to a single hole. All the things I am talking about is nothing related with this black hole, but something I want to say. That's why I've said. Now what happens, suppose so how this, now the question is how this black hole radiates, right? Now the question is how the black hole radiate. As we are discussing that all the things that come into the black hole and crosses the event, it will attract towards the singularity. Now how this black hole will radiate? So this is a great question. So we can see it from that. We all know that the vacuum possesses some energy. Suppose that in some point the vacuum energy will be greater than 2 me c², where the me is the mass of the electron. If the vacuum energy is greater than equal to that, vacuum energy is greater than 2 mc², then in this point simultaneously one particle and one antiparticle will create and annihilate. That means in the same point, two particles, one is electron and another is positron, will be created and annihilated. But suppose that the same thing will also happen on the event horizon. Now if that same thing happens on the event horizon, that means some particle will be created outside of this event horizon and some particle will be created inside event horizon. Which particle, means particle or antiparticle, which created inside the event horizon, they cannot leave this black hole, they eventually hit the singularity. But which will be outside the event horizon, this will be eventually, this will goes in the opposite direction and goes far apart from this black hole. That means this particle radiated from this black hole, and that's how this black hole radiate electromagnetic wave or particles, and that's how this black hole radiate. Now since this black hole has a temperature T, as we discussed previously, that means this black hole, if we consider this black hole behaves like a black body, then we can write that the energy it emitted per second, that means the energy emitted per second per area will be energy emitted per second per area, we know that will be sigma T to the power 4. If the temperature is T, then T to the power 4, and that means the energy it radiates will be minus sigma T to the power 4 into area. Area means area of this event horizon. So that equation should be followed, because that's how it's emitted energy. Now to know how the energy emitted with time, we have to know the area, right? So area. So what will be the area? Now area will be the area of this event horizon. Now what is the radius of this event horizon? Now the radius will be Schwarzschild radius. Radius will be Schwarzschild radius. This radius is nothing but this can be calculated exactly from general theory of relativity, and which is RSH is equal to 2g m. M is the mass of that black hole by c square, and we know that the energy of that black hole will be mass into c square. That means we can write it as 2g, in place of m we can write e by c square, g e c to the power 4. Okay, so that's it. And then area, what will be area? If we assume that this black hole event horizons geometry is spherical geometry, so we can write it 4 pi r sh square. So that means 4 pi 2 g e c to the power 4 its square. That means 4 pi, this is basically 4 pi 16 pi, so will become 16 pi g square c to the power 8 e square. So area will be order of e square, right? Okay, so the area will be square, we know that. Now we have to calculate the temperature. What will be the temperature? As we are discussing the previous to solve the previous question. Now what is the temperature? We know the to calculate the temperature we need the entropy and energy. Now what will be the entropy of that black hole? What will be the entropy of that black hole? Now think for a moment that black hole, all the mass or all the things, all the matter that are inside these event horizons are remain in a single point. So that means, and we can describe that point by only one microstate. That means the entropy of that black hole should be 0 because it's collapsed to a singular point. And if it is a point and in that point all the information is there, that means these black holes, if we consider only this point where the all matter just collapse to a single point, and we can describe by a single microstate, that means the entropy of this single point should be 0 because we know that the entropy will be total number of log of total number of microstate, and microstate will be 1, the entropy will be 0. So that means this singular point contribute nothing. But what can contribute? The entropy can be there because of the black hole does not only, a black hole does not only characterized by its singular point but also the radius, Schwarzschild radius. That means the area which is covered the black hole, the Schwarzschild radius should possess some information about the black hole. It should possess some information about the black hole. And what will be that information? Means if the black hole has an entropy, it should remain on that surface, because as we are discussing at the point where the all mass collapsed, there will be no entropy at all. So if the black hole has any entropy, a black hole has an entropy, it should be entropy of that surface which is there at radius r, at r, means Schwarzschild radius. Now what people thought is that maybe the entropy will be the area by the number of the minimum area physically possible. So LP square. So LP is called Planck's length, and LP square is the smallest smallest possible area. Smallest possible area. Why people thought like that? Because suppose that the information are stored in a in that area, that means one single bit of information should be stored in a single, means in a particular smallest possible area. Now we know that the smallest possibly physically smallest area that we can calculate from using our known constant is actually Planck constant. So that's why you can thought that A is equal to A by LP square, and it's not actually A by LP square, it's actually L by 4 LP square. So the entropy of that black hole is nothing but the area by 4 pi LP square. Now if we put the value of area here, we'll got S equal to 1 by 4 LP square into 16 pi G square C to the power 8 E square. Now we have done, so we can now calculate, since now we know the what is the relation that has been followed by the entropy and energy of a black hole. So the inverse temperature will be then partial derivative of entropy with respect to energy. It will be 1 by 4 LP square into 16 pi G square by C to the power 8 2E. Nothing to worry about. So we will put this constant, suppose then we can write the temperature as a function of energy, or temperature should be a function some constant alpha into energy to the power minus 1. We can write the temperature as some constant in energy to the power minus 1. Okay, so now we know the value of temperature. Now we also know the area, and to simplify the calculation and get rid of this constant, we can write it as a constant beta. Okay, for not to class the coefficient, let it write as, okay, so you don't know Bengali, so that's so it's, let's write in some constant is something, some, okay, some A. Okay, some A is constant, some B E square. So that will be A to the power minus E B E square. Okay, now let's put it there in the formula. So dE dt will be minus sigma into T to the power 4, means A E minus 1 to the power 4 into B area. So area will be B square, so P square. Now we can write it as these, again we can, all this constant we put it simply B into E to the power minus 4 into E square. So that means E square dE dt is actually minus P. So that equation we get. So that's how the energy of the black hole is reduced with time or decreased with time. Now let's solve the energy as a function of temperature, because this is a very simple integration we can do. So 0 to some, okay, not 0 at first, the energy of the black hole was E0. Now it becomes E, what time it's required to reach there, dE is equal to minus B integration 0 to T. At T equal to 0 the energy is E0, at T equal to T E, so T prime. So this will be, okay, there will E square is there, huh? e square is there, so that means e cube minus e0 cube equal to minus bt. So that is e cube is equal to e0 cube minus bt, which will be e equal to e0 cube minus bt to the power 1/3. If we take common e0 cube, so I will get 1 minus bt by e0 cube to the power 1/3, which will be, it's actually e0, okay, e0, this is nothing but 1 minus t by e0 cube by b 1/3. So this will be the energy. So that's how the energy decreases with time. So you can see that as time increases, the energy will be decreases with time. Now if we write the energy in terms of the mass of the black hole, we know that energy will be mc square. So if I write it there, so c square cancelled out, m in a function of t will be the initial energy, and 1 minus t by m0 cube, and this is c6 by b. So now let to the power 1/3, right, m0 cube c6 by b. So mass of the black hole will be decreased in this fashion. So m0 cube c6 by b, I am writing it again, and if we put all the values of the constant, you will get this. Let me check what is the value. Okay, now you will get that c6 by b will be 10 to the power 25, 10 to the power 25 second per gram cube. Now from this equation we can say that at which time the all mass will be evaporated. That time tau is actually m0 cube c6 by b, and what was the mass, what is the mass of the black hole initially? 50 grams. So if we put it there, we'll got 50 cube. So in the order of 10 to the power, in the order of 10, so it's actually in the order of, it's not exact equal, but 10 to the power 25. So we have to calculate 10 to the power minus 25. It's so 10 to the power, no, it's 10 to the power minus, yeah, it's actually 10 to the power minus 25. So this is c6 by b is 10 to the power minus 25. So 10 to the power minus 25 second. So it's 5 into 10 cube, 5 cube into 10 to the power minus 25 second. So okay, let me check it. So it's basically 1/3 should be there, it's calling 1/3 should be there, which I have missed, should be there somewhere. Okay, e square, so e square there will be 1/3, so 1/3, so this will be 1/3, 1/3, so 3 will be sitting there, 3 will be sitting there, 3b is sitting there. So 3b is there also, e cube by 3b, so a 3 should be there also, there also. So a 3 3 is there, so 3 is there, so 3 should be there. So it's order of 1.25 into 10 to the power 5 by 3 into 10 to the power minus 25. So 1.25 by 3 into 10 to the power minus 21, and this is will be 10 to the power minus 10 to the power 20, and 3 by 6 10 to the power minus order of minus 1. So 10 to the power minus 20, it will be order of 10 to the power minus 21. So now we got the answer, at which time the mass will be completely evaporated. Say the value at which time, so the time will be order of 10 to the power minus 21 second. That means 3 to the for 6, answer will be 3.36 into 10 to the power minus 21 second. So that's it. So this was the question number 6 that I have planned to solve today. So basically we have solved all the things, and for recapitulate, so the basic things that I want to again emphasize, that the in statistical mechanics, since in statistical mechanics all the things are stochastic, means we cannot say a quantity with certainty, or in other way, a bunch of a lot of gas molecule moving around here and there inside a box, we can't exactly pin down which molecule is in which state. Which state means each molecule, with each and every molecule, the position and velocity, or position and momentum of each molecule. So to state, to predict or to say something about that kind of system, because in physics we want to say something about every physical system. Now in statistical mechanics, like this kind of system where a lot of gas molecules moving around inside a box, we cannot pinpoint the position and momentum of every particle. If there is a single particle moving around, we can say the physics about that particle, that the particle possesses some momentum, possesses some energy, and at time t it is in the position that position. That means we describe a single particle pretty well. But when there is a lot of particle or molecule inside a box, we cannot say anything about the system, because we cannot say the position and momentum exactly of each particle. So that's why we to describe this kind of system, there is a way. The name of that way is the statistical mechanics. We don't know which particle is where, but we can exactly calculate the probability of the particle remaining at the position at some position at some state. So that is the basic things for statistical mechanics. And since the particles are moving around here and there, so to describe the system we need something in concrete, means we need something which does not change with time. So in equilibrium we actually know that things, we actually know if the system is macroscopically does not change with time, we can say the system is in equilibrium in macroscopical level, and we can describe the system in terms of statistical mechanics. Now if I ask the question, what do I mean by the equilibrium, means when I say that system is in equilibrium with another heat bath, what do I mean by that, means what the microscopic description of that system look like. So this is a legitimate question. So to do so, we have to define the equilibrium very in concrete way. So equilibrium means the detail balance when the system in microscopic level, when the detail balanced will be hold, just when the detail balanced holds, then the system, then we call the system is in equilibrium. Other way we will say the system is in the non-equilibrium state. If the detail balance does not follow for any system, then we will say the system not at all in equilibrium. We will call it in a non-equilibrium state. Now you can see the importance, because to describe the physics of that type of system, we have to define detail balance, and detail balance is the equilibrium what we mean in the statistical systems. So that's why this detail balance is actually very important. And again, the detail balance means the number of forward direction is exactly equal to the number of backward direction. That means the substance or the things, the changing in the forward direction is equal to the reverse direction. That means nothing change at all over the time, and microscopically they look same with time. So the detail balance means, suppose there are three states are there, so detail balance means if something is happening here to there, here to here, exact things should be, and something happening there to there and there to there, then the whole things that change because of this process plus this process plus this process plus this process should be zero. Then we will say that this state or this system is in detail balance. And as we see in the detail balance also means that the system is actually time, system possesses the time reversal symmetry also. So that's all. That's the things I have planned for today. So thank you. So I will now stop this presentation. Okay.